Okay, good morning, everyone. How did the homework go? Can you please post your questions? Pretty good. Okay, anybody besides not very good? Can you do 11 and 13? Yep. Which section? I forgot. I remember I assigned problems from 2 sections. 11 and 13, which section those? 11.5. Okay. All right, any other questions? Please go ahead, feel comfortable. I didn't get 11 from 11.5. Yeah, okay, I'm gonna do both of them, 11 and 13. Okay, I had the same question as Sarah and Con. Very good, so let us start with that. So it's 11, I can start. Okay, so I start with number 11. Okay, and this is section, forgot 11.4. So 10, sorry, I start with 10. And then I will do 11 and the rest. Okay, so start with number 10. 10 tells me the following. We have the following series, sigma minus 1 to the n times 3n minus 1 over 2n plus 1. Okay, and this is sorry, this is an alternating series because those terms are positive. So those terms, if you think about them, those terms are positive. So minus 1 to the n is going to alternate them as far as sign is concerned. So in this scenario, my Bn is 3n minus 1 over 2n plus 1. And the an, it means the actual term of the series. The actual term of the series are the minus 1 to the n, 3n minus 1 over to n plus 1. These are the actual term of the series. The bn are only this positive one after they alternate. And does the series converge or diverge? I always check what's happening to the term as n goes to 0. So if I compute the limit as n tends to infinity of the bn, so this is equal to what? It's the limit as n goes to infinity of 3n minus 1 over to n plus 1. Okay? Now, what's the limit of that as n tends to infinity? Do we know? Very easily. If I divide by n, numerator and denominator, I get 3 minus 1 over n, 2 plus 1 over n. So as n goes to infinity, this is equal to 3/2. So already I know there is a trouble. It means the terms bn, the positive terms, actually become close to 3/2. So the original term of the series, the an, are those going to go to 0? Yes or not? So those terms, will those go to 0? Yes or not? Ideas? Okay, it looks like you're doing 11.5, number 7, not 11. Okay, I'll do this and then I'll get back to whatever I'm doing wrong. Okay, so let's go back. Sorry, whatever. I'll go back. So I'll stick to that. So that's 11.5. Thanks, Sarah. Thanks for telling me this. So this is equal to 3/2. It means the original terms means when I take minus 1 to the n, 3n minus 1 over 2n plus 1. Here I'm wasting 5 minutes. So limit as n tends to infinity of those terms, we know that those become close to 3/2. But having the minus 1 to the n in front makes this one, the limit does not exist. It means my series diverges by the divergence test. So it means this sum diverges. (3n minus 1 over 2n plus 1 diverges by the divergence test. That we can conclude. The terms really blow up. All right. So I'll go back now to number 10. So let me understand. It's number 10, 11.4. Is that correct? Yes. Okay. So I'll go back to 11.4 and then I'll proceed with your other question. So 11.4, number 10. Okay. And this is it. So number 10, it was sigma k times sine square of k over, okay, over 1 plus k, and this is to the power 3. Very good. So this is a series with positive term. It's not alternating, so everything we're doing with alternating has to be pushed to the side. And what is here my general term? As I used k, I'm going to use k for my general term. It's k times over 1 plus k to the power. And the question is, does the series converge or diverge? Now, all right, what do we know? Integral, that's positive. Integral test is basically almost impossible because integral test will make me integrate x sine square x over 1 plus x to the power 3. Absolutely impossible to use. Limit comparison. I usually go through the list in my head. Limit comparison is problematic. What makes limit comparison problematic is that when k is large, what makes it very problematic? Because what's going on when k is large. That's what the limit comparison really deal with. When k is large, I know the denominator is k cubed. I have problem here. Sine square of x, I don't, when k become very large, the sign, what does it do? The sign oscillates up and down. So it's not close to anything. So I don't know its behavior when k is large. That's really the problem with the sign. So limit comparison is going to fail because I don't know what to put here. Is it k? It's not right. It's not k because sine square is not doesn't behave like 1 when k is large. I don't know its behavior. So this is usually the scenario whenever the sign shows up where the ordinary comparison get into the picture. So the question is, how can I use the ordinary comparison? I did something fairly similar yesterday, and it works like this. The sine x, I don't know its behavior, but I know one thing about it, something important. I know that the sine of k is always between -1 and 1. It means when I square this, it's going to be positive for sure, but it's always less than. And that's what I'm going to use to see if I can control this problem. So with this in mind, what's going to be ak? So it's k over 1 plus k to the power 3. Sine square is really my issue. And the question is, can I somehow manipulate that? So it's going to be less than what? The denominator I'm not changing. Sine square is less than 1. So when I multiply it by k, so if sine square is less than 1, k is a positive number. So if I multiply by it both sides, this is going to be less than k. So now my numerator is less than k. Okay, very good. Now I'm going to ask you a question. Do we know how to handle a series where the terms are k over 1 plus k cubed? Do we know how to handle those? I want answer on the chat. If I give you this series, do we know how to check whether it converges or diverges? Either write on the chat, I don't know, or in mute and speak up, I want an answer.
Hey, sorry, I'm using my girlfriend's computer, but it's a limit comparison, is it not?
It's a limit comparison, absolutely correct. I don't care which computer you use, as long as you answer. Okay, so it's absolutely, it's the limit comparison test. That's the one to do. But, so I know how to do that, limit comparison. But, okay, but I'm gonna ask you a little bit, push you a little bit further. Is this less than something easier? Can I push a little bit more? 1 over k squared, right, because this is k is the same, because I can in this problem. 1 plus k cubed, not it, 1 plus k cubed is definitely larger than k to the power 3, right? So since the denominator is larger, this is going to be less than that, which is 1 over k squared. And this is going to be my bk. So you can proceed 2 ways in this problem. Either you stop right there. You call this your bk, use the limit comparison, convince me that this one converges, and then conclude that sigma ak converges by the comparison test, ordinary one. Or you push yourself a little bit more because we can, not because we can, and say, you know, I can push myself a little bit more and this is less than 1 over k squared, and choose bk to be 1 over k squared. So now I have ak is less than bk. But what do we know about bk? And everything is positive. Now, sigma bk is sigma 1 over k squared. This one converges because it's a p series, p equal to 2. So the larger one converge. If the larger one converge, the smaller one being positive, it cannot go to minus infinity. It's going to really be also conversion. So the larger converge, it means that the smallest series, which is the one I'm interested in, also converges. Okay? Questions about this problem? Right. So which other problem? I now lost track with the chat. I will do one more problem. Which one? Let's see which one you guys asked to do. I have to back up. 11.11 or 13. Okay. So let's look. Okay, let's look at number 13. All right, so I have the following. Sigma -1 to the n minus 1 e 2 over n. That's 13, right? Yeah, n equal 1 to infinity. And the question is, does the series converge or diverge? Now, is this alternating? I mean, we have really to recognize, if I want to use alternating series test, I want to make sure it's alternating. Is this alternating? Yes or no? And what makes it alternating? You have to give me a reason why it's alternating. What are going to be the Bn? It's alternating. We want those to be the Bn. E to the 2 over n. Are they positive? And it's crucial, because if those are not positive, this will not alternate. So the term that comes next to -1 has to be positive for this series to alternate. But e to any power is a positive number. E to any power, because that's how the exponential works. E to any power is positive, which makes this series an alternating series. It's going to become minus, plus, minus, plus. Because if those Bn are not positive, it will not necessarily alternate. So now we're going to go through the alternating series test and see what's really going on. So let me go to the limit as n tends to infinity of the Bn. And let's see what's happening to those. So that's the limit as n tends to infinity of e over 2 to the n. All right, what's the limit of those? I want answers. Analyze it. Tell me the limit. Please, all of you have to participate. Okay, I'm getting 1, 1, 1. Everybody is correct. As n goes to infinity, 2 to the n goes to 0. E to the 0 is equal to 1. So those terms Bn are actually not becoming close to 0 at all. It means the initial term of the series, so we're back to the same issues. So now it's as a rule, when the Bn don't go to 0, it's going to diverge. So the original term, so when I look at the An themselves, what's going to happen? The terms e to the 2n will become close to 1. But when I'm starting to multiply them by -1 to the n, I'm going to have this dichotomy. The term, the even one, will go to 1, so the even, and the odd will go to -1. So those limit does not exist. So the divergence test tells me the series diverge. Right, so both those examples work in a way that the series diverge, and this was caused by the fact that the Bn are not becoming close to 0. Then when I'm putting -1 to the n in front of them, the terms are not becoming very small. Actually, they are hanging around 1 and -1, and the series will diverge. Right, I will look very quickly at number 11. and then I will proceed to the new material. So number 11, I will just look at it and talk about it. So let's look at number 11. I have the following: sigma minus 1 to the n plus 1 times n to the power 2 over n to the power 3 plus 4, I think. Correct. N equal 1 to infinity. First, I would like to make sure that I am dealing with series with positive terms. Sorry, I'm dealing with an alternating series. To make sure we're dealing with alternating series, I want to make sure that those terms are positive. Because if those terms are not positive, if some of them are negative, then the series will stop alternating. So my Bn here are going to be the n squared over n to the power 3 plus 4. And those are absolutely positive. It means we're dealing with alternating series. Okay, very good. So we have to check. To check for alternating series, the test is easy. So first I'm going to check the terms. So does those goes to 0? Oh. N squared over n to the power 3 plus 4. So as n tends to infinity, this is absolutely, as by now we've done it, we divide by n to the power n squared both. I would get 1 here, sorry, n cubed, 1 over n, 1 plus 4 over n to the power 3. As n goes to infinity, this goes to 0, this goes to 0, I will have 0 over 1, which is equal to 0. So it definitely, condition 1 is satisfied. Now, what is the second condition here? Second condition is, are the Bn a decreasing sequence? So this is my Bn, n squared over n to the power 3 plus 4. And the question is the Bn decreasing? Okay. Now, yesterday I did 2 types of problems. The first one, I gave you an easy Bn. If my memory is correct, I forgot what was it, but it was something like that. Suppose I have 1 over n plus 1 to be my Bn. Showing that this is decreasing was fairly simple, because if I take Bn plus 1 is 1 over n plus 1 plus 1. So intuitively, when n gets larger, the denominator getting larger, 1 over the denominator is going to get smaller. So if I have a simple scenario like this, to show decreasing is easy. I can tell you, okay, n plus 1 is absolutely larger than n plus 1, because this n plus 1 bigger than n. So when I'm going to flip them around, it's going to be less than that. It means Bn plus 1 less than Bn. So in this scenario, decreasing is easy. In this scenario, decreasing is not easy at all, because when n becomes large, the denominator gets larger and the numerator getting larger. So it's a little bit harder. So in those problems, we associate to them the function f of x equal x cubed plus 4. And we show that it is decreasing, either by finding the derivative and show that the derivative is negative when x, or sometimes we can just graph it to make life a little bit easier for us. We can pick our calculator and graph it, and we're going to realize when we graph it that the function is actually decreasing. So this is f of x equal x squared over x cubed plus 4. So if we graph it, we realize that the function is decreasing. So this is a decreasing function. So if this is decreasing, then Bn is nothing more than the value that the function is taking at n. Bn plus 1 is nothing more than what the function is taking at n plus 1. So if f decreases, it means that the value at Bn plus 1 is definitely sorry. The value at Bn plus 1 is less than the value at Bn. because this is n plus 1, this is n, and this is n plus 1. The output here is definitely larger than the output here. So if the function is a little bit complicated like that, to show decreasing, you take the function x over xu plus 4, and you show that this function is decreasing. It means my sequence is also decreasing because my Bn is what the output of f at n, the n plus 1, the output at f as n plus 1. Since f is decreasing, the output at n plus 1 is less than the output at n. So now this is a series that satisfies both conditions. That's alternating. Crucial. The Bn becomes close to 0, and then at the same time, the Bn form a decreasing sequence. The alternating series tests that tell me under those two conditions, if those two conditions are satisfied, my series immediately converges. So my series converges. Okay. So let me sum up. How do you show that it is the sequence Bn is decreasing? So you have two ways. If it's simple, you just look at it and try to compare the terms like I'm doing here. If it's something hard like that, to show it's decreasing, you take the function associated to it, you graph it, and you convince yourself that the function is decreasing, causing the sequence itself is decreasing. And what we care about, what we care about is decreasing eventually. I mean, we care about eventually it decreases. What happened at the beginning are not really very important. What matters is what happened at the end, not what happened at the beginning. Right, any other questions before we proceed? Okay, so before I start a new test, I want to spend like a few minutes just to tell you, I promise you that why the alternating series test work, because it's interesting, it's simple, interesting geometrical argument. And then we proceed to the new section. So let's see what alternating series tests. You don't have to write, but just, you're not writing anyway, so just listen a little bit. Suppose you have an alternating series. It means that's alternating. That's the format. That's alternating. Plus, all the b's are positive. And suppose this alternating series satisfies the following condition. The term go to 0. And the sequence of terms decrease. Why those two conditions guarantee that this series actually converge? But let us remember, what does it mean for a series to converge? Series converge, it means the sum of the terms become close to a fixed number. That's what it means for a series to converge. So now my question, why those two conditions guarantee that those sums actually get close to something? They don't blow up. So let us compute the sums, or let us visualize the sum. So again, emphasize the idea. Series converge mean we're adding, and we're asking ourselves what happened to the sum. So S1 is B1, S2 is B1 minus B2, S3 is B1 minus B2 plus B3, S4 is B1 minus B2 plus B3 minus B4. And let us say why those sums are going to become close to something. And let us do it purely a picture-wise. Okay, on number line, I'm going to show you the sum. S1, so this is my 0 here. S1 is B1. Do you guys see well? That's S1. What is S2? It's B1, but you're going to take away B2 from it. And be careful. My condition is that the Bn, so assuming those two conditions are satisfied, it means B2 is actually less than B1. So what is S2? It's S1, sorry. It's S1, but you're going to take away B2 from it. So I'm going to draw B2 here. So this is S1, and I'm going to take a little bit B1 is from here to here. B2 is less. So B2 is going to be here. So what is going to be my S2? My S2 is right there. It's B1 minus B2. Now what is S3? Let me go back. What is S3? It's B1 minus B2, which is basically S1, sorry, S2 plus B3. And remember, B3 is less than B1. So let me draw it on a picture. So where is S3? S3 is S2, but we added B3 to it. So this is S2, we added B3, but B3 is less than B2. So S3 basically is right there. That's S3. What is S4? Can you visualize it? Where is S4? S4 is S3, the previous sum, but we're going to take away B4 from it. That's what S4 is. It's what S3 was, we're going to take a little bit. Can we visualize S4? Remember, the B's are decreasing. So what is S4? It's S3, you're going to take away B4. My S4 is going to be here. What is S5? S5 is S4, you're adding B5 to it. So S5 is going to be S4, but you're going to add B5 to it. S5 is going to be right there. So what's happening to those sums? Are they blowing up or they are getting close to each other? S6 is we're going to add a little bit. S6 is going to be here. Realize the sums, S4, S7 is going to be here. But those Bn are becoming very small. They are going to become close to 0. All those Bn are going to 0 because we have two conditions. So those partial sums are eventually going to accumulate near a specific value. And that would be the sum of the series. There is no room for them to actually go to infinity. There is no room for them to go anywhere. They will have to accumulate because each one, that's the picture. They're going to accumulate somewhere in here, and that's the sum. So alternating series converge under those two conditions because that's actually the picture why this is happening. Those partial sums are going to really get closer and closer to each other. They are getting very, very close to each other. They are getting very close to each other. That's why it converges. Okay. Any questions? All right, so
I have a quick question.
Please go ahead.
So for number 11, the first term, when you have n, when n equals 2, it's actually the term Bn is greater than the first one, but then every term after that is less.
That's what we care about.
Okay, that's what you care about. Is like, okay.
Absolutely. What I thought you care about the end.
Okay.
The first few terms, who cares? What I really care about is what's happening at the end when I'm starting eventually adding those terms. What's really happening at the end? Okay, answer your questions. The first few terms never really matter. It's what happened eventually that matters for us. All right, any other questions? So let us sum up what we've seen so far. And so far, okay, we've seen, as I said at the beginning, finding the sum of a series is a fairly hard problem. But if we know that my series actually converge, if I have this knowledge, then basically I can use our computer algebra system or anything to find the sum. Because I know that it converges, so I start adding and adding until I realize that the terms are becoming close to something. And this is the sum. That's really what it is. But knowing it converges, it helps me a lot. So what we emphasize basically is, since finding the actual sum is hard, we emphasize tests to tell us whether the series converge or diverge. And so far we've seen the following test. We saw the divergence test, which is does not occur a lot, otherwise the problem, which tells me that if the terms don't become small, then immediately the series diverges. Then we saw 3 tests, and all our tests were valid when the series have positive terms. So series with positive terms. And we saw 3 tests. The integral test, when we compare the terms to an integral. The limit comparison test, where we study the behavior when n goes to infinity. And the ordinary comparison test, where we compare our series term by term to another series. And then yesterday, so all those work for series with positive terms. So the question is, we have a lot of other series. What if the terms are not necessarily positive? So today we took one situation, which is the alternating, very particular type of series. Very particular type of series. And for alternating series, we studied a test which tells us when they converge or diverge. But we still haven't basically considered the other problems where, you know, the terms are not necessarily alternating. You know, they can be sometimes positive or negative. So today we're going to see another test called the ratio test. It's a very important test. It does 2 purposes. First, it doesn't care about the sign of the series, whether positive or negative. But another important task it does, a lot of time, limit comparison doesn't work, ordinary comparison doesn't work, integral test doesn't work. The ratio test, sometimes it helps me. Let me give you an example. Before I state the test, I work with it. So suppose I have the following series. N times 2 to the n over 3 to the n. Okay, 1 to infinity. So this is not alternating. So the alternating of the picture. So my general term here is n times 2 to the n over 3 to the n. Integral test absolutely out of the picture, because integral test will have to deal with x, 2 to the x over 3 to the x. Nobody knows how to integrate this. Limit comparison, what is the problem with it? When n is large, what's going to happen? The denominator is 3 to the n. What about the numerator? Remember, we are multiplying here. What shall I compare it with? That's the problem. This is n times 2 to the n. When n is large, n times 2 to the n is not close to 2 to the n, because if n is a million times 2 to the n is not 2 to the n, because you're multiplying here by a million. So this term, if n, like say a million, is a million times that. This is not almost 2 to the n, because you're multiplying it by a million. Versus if you have n plus 2 to the n, this could be comparable. But when you multiply, you're taking 2 to the n, you multiply it by a million. So this will be a question mark. I cannot use the limit comparison. So the question is there a test that will help me out? And that's what we're going to be talking about today, the ratio test. It takes care of problems where the limit comparison don't work. And it works if the series have positive or negative terms. So let us state the ratio test. So I read it very, very carefully, and then I will do 2 examples. What does it say? It tells me the following. Suppose sigma an is a series, and this time I'm not assuming the terms are positive. And let rho be the following. The limit as n goes to infinity of the ratio, and that's where the word ratio coming from, of the absolute value of an plus 1 over the absolute value of an. So the ratio test requires that we take the absolute value of the terms. If the terms are positive, I don't have to worry about it. Then the ratio test tells me the following. If this ratio is less than 1, the series will converge. if the ratio is bigger than 1, the series diverges. If the ratio is 1, this test is inconclusive, meaning the series may converge or diverge. Another test is in order. Okay, so the ratio test should remind us the geometric series in a way. So it tells me that you take the ratio and you analyze, depending on the number you get, you can conclude whether the series converge or diverge. Of course, it has an issue. If you compute the ratio, you get 1. This test is hopeless. We have to do what we've learned before to check the conversions. Immediately practice. So I'm going to start with the following test. Here. And this is my series. Sigma m squared over 3 to the n, 4 to the n. Can you see well, or do you want me to write bigger? Anybody? Okay, so I'll write bigger since you don't answer me. So I'm gonna take, that's my series. N squared, 3 to the n over 4 to the n. And I'm gonna use the ratio test. How do we use it? Okay, I'm gonna look at an. What is an here? My term is n squared. So this is a series of positive terms, and the limit comparison get me nowhere. What is an plus 1? An plus 1 means the term that should come after an. So what is an plus 1? Everywhere I have an n here, this is n plus 1 squared. 3 to the n plus 1 over 4 to the n plus 1. That's what an plus 1 is. It means what the term that should come after an. So if you have a simple series, sigma 1 over n, because that's simple, so this which is 1 plus a half plus a third, etc. 1 over n, that's an, that's 1 over n plus 1, the term that comes up. Now, the ratio test requires that I take the ratio between those terms. So I'm going to look at the following. The limit, so that's rho, that's my ratio. Limit as n tends to infinity of an plus 1 over an. Basically, an absolute value. In this scenario, the absolute value doesn't matter because my series has positive terms. And it looks fairly complicated, but actually it's easy. So that's the limit as n tends to infinity of. I don't need absolute value because it's positive. An plus 1. What is an plus 1? N plus 1 squared, 3 to the n plus 1 over 4 to the n plus 1. Verbatim. What's an? It's n squared, 3 to the n over 4 to the n. Now, I want to compute the limit of the ratio. I know that you look at it and say, wow, but it's not a wow. That's the, so that's the limit as n tends to infinity of. So I have one fraction, basically, divided by another. And nobody would leave something like that in front of them. So we're going to use basic algebra. Times 4 to the n divided by n squared 3 to the n. All right? Now I want to find this limit. It looks like a mess. I know that. But we're going to make it looking very, very, very simple. So what I'm going to do is I'm going to take this limit and I'm going to put the easiest way to compute the limit is to put what I call like term together. So we know how to simplify it. Basically, I want to simplify this expression. So let's see how I'm going to simplify it. I'm going to rewrite this as n plus 1 over n squared, like term together to be able to work with it. And the 3 to the n plus 1 over 3 to the n, just to make it easier, and 4 to the n over 4 to the n plus 1. All right, what's the benefit of that? Let's see what's the benefit. All right, can anybody see the benefit of writing this way? Anybody tell me what I'm gonna do? All right, I'm not gonna touch this first piece. I mean, I'm gonna touch it because I can. This is, I'm not doing, I put the square all together. Now, 3 to the n plus 1 over 3 to the n is equal to what? I want answer in the chat. Can anybody tell me? 3 to the n plus 1 over 3 to the n should give me what? Should be absolutely give me a 3. Because I'll do that on the side because you're going to be doing that a lot. 3 to the n plus 1 over 3 to the n, you can think about it two ways. So let me put it here. I'll explain it here. Right. 3 to the n plus 1, I can write it as one way, 3 to the n times 3. Is this correct? Because you're adding the power. So when I take 3 to the n plus 1, I divide it by 3 to the n. This is going to be, 3 to the n times 3 over 3 to the n. Those and those simplify, we get a 3. So that's one way you can think about it. Another way you can think about it is the following. 3 to the n plus 1 over 3 to the n. You use the property that we know about exponent. It's 3 to the power. You take away the power. 3n plus 1, which is, minus n, because you take the power of the numerator minus that. So an over am is a to the power n minus m. That's what I'm using, basic algebra, which is going to give me equal to 3. So this is important. Why it is important? Because we're going to use this a lot. So 3 to the n plus 1 over 3 to the n, this is going to give me a 3. This is gone. 4 to the n over 4 to the n plus 1, I'm going to use the same trick. This is 4 to the n, and this I'm going to write it 4 to the n times 4. By doing this, those will simplify. And then I'm left with the limit as n tends to infinity of n plus 1 over n squared times 3 times basically 1 over 4. So you can see that it looked complicated, but it's not once you put the like term together and we start simplifying. So finally, what this limit is going to be. Can we see it now? When n goes to infinity, n plus 1 over n, by now we know it's going to go to 1. So this term goes to 1. And then I will have 3 over 4. This is definitely less than 1. The ratio is less than 1. So by the ratio test, the series converges. Okay, so that's how we use it. All right, I'm going to do one more example. It's also crucial. And then, so ratio test is usually easy to apply, even though it looks really problematic. It's easy to apply. Of course, it has an issue when the ratio is 1, and we will talk about that tomorrow. But for now, I'm going to talk I'm going to give you another example. But to start this example, I have to take you back to definition. So I'm going to talk a little bit about factorial. Okay, tell me if you guys are familiar with it or not. So, okay, I'm going to skip 2 lines. I'm going to start here. And then what is 2 factorial? Do you guys know what the factorial notation is? Yep, yep, yep. It's 1 times 2 equal to. What is 3 factorial? It's 1. You keep multiplying times 2 times 3, which is 6. 4 factorial. It means you keep multiplying 1 by 2 by 3 by 4. So you keep multiplying till 4. Okay, that's 24. And the picture continues. 7 factorial, let us say. I skipped. It means 1 times 2 times 3 times 4 times 5 times 6 times 7. So that's what factorial is. 1 factorial is 1, and 0 factorial, which is problematic, is also equal to 1. So that's the one you should be careful with. Now, so in general, n factorial is you keep multiplying, etc., up to n. That's the last term you multiply by. Now, before I do my example, I'm gonna say one thing because we're gonna use this fact a lot. I'm gonna go back to 7 factorial before I state my result. How can I relate 7 factorial to 6 factorial? Can anybody tell me? I want to find a relationship between 7 factorial and 6 factorial. What's the relationship between them? I drew the picture so you guys can see. Anybody can see what's the relation you can build between 7 factorial and 6 factorial, the terms before. So I'm seeing one answer. Do you agree with? Absolutely. This is 6 factorial times 7. Why this is important? It means if I have n plus 1 factorial, how can I write this in terms of n factorial? Okay, can anybody give me the answers on the chat or speak it up? So I want it in terms of n factorial. Let's see, what's n plus 1? It means you keep multiplying, ding, bing, bing, and the last term has to be n plus 1. Right. So what should be the term before it? It should be n. This is like I did up here for 7 factorial. This piece is n factorial times n plus 1. So n plus 1 factorial is n factorial times n plus 1. So of course, why I am bringing this into the picture, because we need it a lot. The factorial is gonna play a role for us. Okay, sorry. So my last example is the following. Again, I'm gonna use the ratio test. And the question is, I'm going to take a simple one because we don't have 2 to the n over n factorial. Actually, I'm going to start from 0 to infinity. One of the extremely important series, and later on we're going to show that's actually, we know the sum of this. We're going to show that this is equal to e squared. E is the e, and we're going to show that this is actually equal to e squared. Means if you start adding the sums of those, you get e squared. That's a good exercise for you tomorrow. Try and show me that this is the case. All right, so here it means basically it's if n equal to 0, I'm starting at 1, n equal to 1 at 2 plus 2 squared over 2 factorial. That's really the series I'm looking at. Over 3 factorial, 2 to the 4 over 4 factorial, and so on and so forth. That's really what I am looking at. And I'm gonna show you that it converges using the ratio test. So what is an here? 2 to the n over n factorial. What is an plus 1? Is everywhere I have n, I should have n plus 1. It means 2 to the n plus 1 over, instead of n, you have the expression n plus 1 squared. So that's what it is. Suppose n equal 2, 2 square over 2 factorial. If n plus 1 will become 3 over 3 factorial. And let's compute the ratio. So in both examples, I'm giving you series with positive terms because, it's the ratio test is useful all the time. So I'm going to take absolute value of an plus 1, that doesn't really, which is an because an is positive, and I'm going to compute the ratio. So that's the limit of, what's an plus 1? 2 to the n plus 1 over the quantity n plus 1 factorial over 2 to the n over n factorial. I will do exactly what I did in the previous problem. It's going to give me 2 to the n plus 1 over the quantity n plus 1 factorial times n factorial over 2 to the n. And then I want to simplify. So I put like term together just to make it a little bit simpler for us to visualize what's happening. So I'm going to put 2n plus 1 over 2 to the n times n factorial over that. All right, we're almost at the end. So it's the limit as n tends to infinity of 2 to the n plus 1 over 2 to the n. We just saw it a minute ago. So one way, as I said, you write it 2 to the n times 2 over 2 to the n, so you can simplify. And this, n factorial over n plus 1 factorial, does really look like a nightmare, but it's not. Because of the relationship between n plus 1 factorial and n. And that's what we've talked about. N plus 1 factorial is n factorial, because you multiply up to n, just give you the n factorial, then times n plus 1. That's why we need this. Now let us simplify. Those go, we knew that. N and n factorial simplify, so I will be ending up with the limit of 2 over n plus 1. As n goes to infinity, this is going to be equal to 0. Now, what does the ratio test tell me? If the ratio is strictly less than 1, the series will converge. So this is a 0, which is of course less than 1. It means my original series will converge by the ratio test. So my original series will converge. Will actually converge. It means if we start adding those sums, we're going to get to a real number. It's a fixed, it's not going to blow up to infinity. And as I said, actually, you guys, if you want to have sometimes free, this is going to be e squared, which is like almost 7 point something. So if you guys take the sum, start adding terms, adding terms, adding terms, and adding more terms, you're going to realize you're going to get closer to e squared. So that's really what does it mean for a series to converge? It means those sums are getting close to something. And that's the number that we'll get close to. All right? At this note, I finished today's. Any questions before we move on? All right, guys. To remind you that I have, can you move the paper down this way? Can you move the paper down this way? This way? Is this Sarah? Yes. Okay. Good. Anything else? As you guys know, also I'm recording it and I'm putting the recording on Blackboard. I usually put it in the evening when I have time to do it. And again, I have office hours, as you guys know, right after class. And please, if you have questions, join me during my office hours. I don't stay in front of my computer. I go back and forth in the house, but still, please join me if you have any questions. All right? Okay, bye-bye for today. Talk to you tomorrow.